Fundamentals of Probability, Chapter 7. In this chapter, we are going to understand the definition of probability, the theorems of probabilities, and the counting of events rules. And also, we are going to cover the discrete probability distributions and continuous probability distributions. So let's start defining probability. And to do this, you need to be familiar with other terms used for probability, and these are likelihood, chance, tendency, and trend. So whenever you hear these different terms, they are referring to probability. So probability is defined as the chance that something will happen. Okay, for example, I will probably play soccer tomorrow. It will probably rain tomorrow, or the probability of rain tomorrow is 25%. Or if a nickel is toast, the probability of a head is 1.5, and the probability of the tail is 1.5. So probability is related to the outcome. Okay, for instance, in that nickel, you always have two possible outcomes. You either have the head or the tail when you toss it, right? So the probability is associated with the outcome that you are expecting. Also, when we go over the different distributions, you need to be aware that the area of each distribution is equal to 1. And we saw this when we were working with a normal distribution curve, and we were using the Z formula. So the area under the normal distribution curve is always equal to 1. And that was the way that we could find or solve those problems. So the total probability of any situation will be equal to 1 as well. Now, probability is expressed as a decimal, okay? Instead of saying 1.5 for the head or 1.5 for the tail, you can say the probability of the head is 0.5. And as I mentioned before, probability is associated with the outcomes. And an event is a collection of outcomes. For example, if you have a 6-sided die, and this has 6 possible outcomes because it has 6 faces, and each face represents a number, 1 through 6. So when the number of outcomes is known, or when the number of outcomes is found by experimentation, the probability of an event A is equal to the number of successful outcomes of event A divided by the total number of possible outcomes. So this is another definition of probability. So the probability calculated using known outcome is what we call true probability. And the one calculated using experimental outcomes is different due to the chance factor, because it could happen or not. Now, when we have an infinite situation, the definition will always lead to a probability of 0. And this is when you don't know the outcome of the outcomes has infinity numbers of occurrence. So now that you're familiar with the definition of probability, let's now review the different theorems of probability. So theorem number 1 says that probability is expressed as a number between 1 and 0. And usually in probability, we use 3 decimal places. So this will be 1.000 and 0. Okay, where the value of 1.000 is a certainty that an event will occur, and a value of 0 is a certainty that an event will not occur. Okay, so now you know that probability is always a number between 1 and 0, and that's why you can express the probability using decimal places. Now, when the probability is close to 1 or is equal to 1, you're more certain that a situation will happen, when this probability of 0 or close to 0, the chance that will happen is now minimum. Theorem number 2 says if the probability of an event A is the probability that the event A will occur, then the probability that A will not occur is 1 minus the probability of occurrence. Okay, and for instance, if you're trying to find the probability of finding an error on a income tax return, and you know that that probability is equal to 0.04, so what is the probability of finding an error-free or conforming return? It will be 1 minus 0.040, which is 0.960. Okay, or it also could be expressed in a percentage, which you will see is 96%. So if you want to find the probability of an event will not occur, you just subtract the probability of occurrence from 1. Now, to understand theorem 3, 4, 6, and 7, you need to be familiar with two different situations. One is that you have one event out of two or more events, and you have mutually exclusive or non-mutually exclusive events. So when this happens, you follow either theorem 3 or theorem 4. Now, if you have two or more events out of two or more events, then you will follow 6 and 7, and these depend if you have independent events or dependent events. So let's review theorem number 3. And this has to do when you have one event out of two or more events. So theorem number 3 says that if A and B are two mutually exclusive events, and this means that the occurrence of one event makes the other event impossible. For instance, if you're having one baby, you know, the fact that you have a baby girl is already, these are two mutually exclusive events, because if you have one baby girl, it's impossible that you have a baby boy, because there's only one baby. Okay, so what happened in this case, the probability that either event A or event B will occur is the sum of their respective probability. And this is what we call the additive law of probability. So the probability of A or B is equal to the probability of A plus the probability of B. Following the same example of having the baby, so you have 50% chance of having a baby girl and 50% chance of having a baby boy, right? So if you add them together, this will be equal to 1. And remember this, the sum of all the probabilities is always equal to 1 for the same event, which is the probability of all the possible outcomes. So whenever you see an OR, this means that you have a mathematical operation, which is the addition. Okay? So now let's understand theory number 4. This one is for not mutually exclusive events. So this means that if an event A and event B are not mutually exclusive, and this means that the occurrence of one event doesn't make the other event impossible, then the probability of either event A or event B or both is given by the probability of A plus the probability of B minus the probability of both. Okay, and I will say that this is in the case that you are expecting twins. So you can have either both being a female or both being male. Or then what is the difference if you have one of each? Okay, so when we're talking about events are not mutually exclusive, is because they have some outcomes in common. And this is where the Venn diagram concept is in place, is when you have the two circles, and the two circles, both area touches in one place. So that is the probability of both outcomes for one event. Okay, theory number 5 is not part of this two different situation. Theory number 5 is just says that if sum of the probability of the event of a situation is equal to 1. Okay, once again, so you have the probability of A plus the probability of B plus the probability of N for one event is always equal to 1. Theory number 6, and this has to do when you have two events or more, right, out of two or more events. And theory number 6 says that you have to have independent events. So if A and B are independent events, and this means that one in each its occurrence has no influence of the probability of the other event or events, then the probability of both A and B occurring is the product of their respective probability. Okay, so the probability of A and B, see we're using a different quotation N, this is equal to the probability of A times the probability of B. So this theorem is referred to a multiplication, and this is what we call the multiplicative law of probability. And this is whenever you see that N. Okay, theorem number 7 is about dependent events. So if A and B are dependent events, the probability of both A and B occurring is the product of the probability of A and the probability if A occurred, then B will also occur. Okay, so this is equal to the probability of A times the probability of B slash A, which is defined as the probability of event B provided that event A has occurred. Okay, so a dependent event is one of, whose occurrence influences the probability of the other event or events. Okay, these theorem number 7 is sometimes referred to the conditional theorem. And this is because the probability of the second event depends on the result of the first event. And remember, this is only if you have more than 2 events. So now let's review the different counties of events rules. And to understand this, just know that many probability problems, such as those in which the events are uniform probability distributions, and this is just a type of distribution that is constant, this type of problems can be solved using counting techniques. And they are 3 counting techniques, and they are they're commonly used in the computation of probabilities. So these are the simple multiplication, the permutations, and combinations. So let's start understanding simple multiplication. And this is when you have, if an event A can happen in any of A ways or outcomes, and after it has occurred, and another event B can happen in B ways or outcomes. So the number of ways that both events can happen is A times B. Okay, and to give an example of this, let's say that you have a witness to a hit and run accident, and this person remembered the first 3 digits of the license plate out of 5, right? And also he noticed that the fact that the last 2 were numerals. So how many owners of cars will the police have to investigate? So this is a simple multiplication. So you have A and B. A being 10 is because you have numbers that go from 1 to 10, or from 0 to 9. And also you have another situation and this is for the 2 numerals that the witness saw. So you have 2 possible situations there. So you have 2 possible 10 times 10, so that's 100. Okay, you also, the person remembers that the last two were letters. Okay, in this case, you know that the alphabet has 26 letters, so A is 26 and B is 26, so 26 times 26 is 676. So those are the different cards that the police have to investigate. 1 for numbers, or 100 for numbers, and 676 for letters. Okay. Another counterintuitive rules is the permutations. And a permutation is defined as an ordered arrangement of a set of objects. It's represented by this formula in which the number of permutation of any n objects taken r of them at a time is equal to the factorial of n, or n factorial, which is the total number of objects, divided by total number of objects minus the number of objects selected out of the total number, factorial. And to give an example is if you have the word cup, because the permutation is refers to the ordered, the way that you arrange those objects. So you can have CUP, you have 3, right? Or you can have CPU or UPC, UCP, PUC, and PCU. So you can, the permutation, you can permutate this 6 times. Combination is another counting of events rules, and this is when the way that the objects are ordered is unimportant. So this is when we have combination, and this defined as the number of combination of n objects taken r at a time is equal to n factorial, which is the total number of objects, divided by r factorial, which is the number of objects selected out of the total number, times n minus r factorial. And using the same example of the word cup, we know that it has 6 permutations when the 3 objects are taken 3 at a time. Now, there will be only one combination, and this is because the same 3 letters are in different order. So the order is unimportant. So now let's review different probability distributions, and let's start with the discrete probability distribution. And remember, discrete is because we're using discrete data. And this is when specific values such as the integers 0, 1, 2, 3 are used. You cannot measure, you cannot break into decimal places discrete data. Okay, we're going to be reviewing 3 different types of distribution, of discrete probability distribution, and these are the hypergeometric, binomial, and Poisson. So let's start with the hypergeometric. And the importance of this review is that you understand the different characteristics that are unique to each distribution type. So for the hypergeometric, you need to understand that they occur when the population is finite, and the random sample is taken without replacement. So this is very key. You have a total number, so you have the population value, and you also, every time that you take something out of that population, you not replace it. So this means that the probability of that whole population is always changing. Okay, so this formula is constructed of 3 combinations. You have the total, you have non-conforming, and you have conforming types. Now, the numerator, if the possible ways or outcomes of obtaining non-conforming units times the possible ways or outcomes of obtaining conforming units. And the denominator is the total possible outcomes. Now, for instance, if you want to find the probability of 2 or less, the way that you have to do it using the hypergeometric is you have to find the probability of 2 minus the probability of 1 minus the probability of 0. Remember, we're using integers, and this is because this is a discrete data. Now, you can also approximate this type of distribution to the binomial, and this is when n divided by n is capital N, which is the population size, is less than equal to 0.10, or also can be approximated to the Poisson, and this is when sample size or divided by the population size is less than equal to 0.10, or when you have the proportion, the PO, less than 0.10, or Einstein P less than equal to 5. But you also can approximate it to the normal distribution, and this is when n divided by n is equal or less than 0.10, and this is and from here you can approximate it to the binomial. So it's always good to understand that you can treat them as a different type of distribution, because in some cases it's easier to work with a specific distribution type. And this is the formula that we use, and is the probability of the non-conforming units in a sample of size n is equal to the combination of non-conforming units, which is the C, D, and D, times the combination of conforming units, which is the C and capital N minus D and small n small minus small d, divided by the combination of all units. So once again is a combination of a total non-conforming and conforming units. Okay, a second type of discrete probability distribution is the binomial distribution. And this type of distribution, once again, is applicable to discrete probability problems that have an infinite number of items, or that have a steady stream of items coming from a word center. So this is different from the hypergeometric, because now we have an infinite number of items. Okay, so as the sample size gets larger, the shape of the curve will become symmetrical, even though P is not equal to Q. So the probability of having a successful outcome is not equal to the probability of having a failure. Now, it is required that there be two and only two possible outcomes. So you have either a conformity or a non-conformity, and that the probability of each outcome does not change. So this is what it makes it different from the hypergeometric. The probability is constant for each outcome, and you have infinite population size. In the hypergeometric, you have finite, and then you have your probability of the outcomes were not constant. So to use the binomial distribution, this requires that the trials be independent. Also, this distribution can be approximated to the Poisson and to the normal distributions. Now, the last distribution for the discrete probability is the Poisson probability distribution, and this is the characteristics. It is applicable to many situations that involve observations per unit of time or observations per unit amount. And in each of the preceding situations, there are many equal opportunities for the occurrence of an event. So these are the three characteristics: observations per unit of time, observations per unit amount, and many equal opportunities for the occurrence of an event. Now, it is applicable when n is quite large and P sub O, which is the proportion, is small, okay, which is the average count or average number. Now, when the Poisson is used as an approximation to the binomial, the symbol C has the same meaning as the D has in the binomial in the hypergeometric formula, which is the count or number of events of a given classification occurring in a sample, such as the count of nonconformities, for example, cars, customers, machine breakdowns, etc. Now, when n times P sub O, which is the average count or the average number of an event of a given classification occurring in a sample, gets larger, the distribution approaches symmetry. And for this type of distribution, you can use a table, and this table C in your appendix. Now, this type of probability is the basis for attribute control charts and for acceptance sampling that we're going to see later on in this semester. It's also used in other industrial situations, such as accident frequency, computer simulation, operation research, and work sampling. Okay, and other type of discrete probability distributions that were not covered today but are part of the discrete probability is the uniform, which is generated a random number table, which is that the ones that the probability is constant. You got the geometric, and you have the negative binomial, and this one is used for reliability studies. So going back to the use of the table C, so the Poisson is can be easily calculated using table C in your appendix, and it has similarity among the hypergeometric binomial because it is using the same type of components for the calculation. Now, the formula of the Poisson distribution is BC equal to NPO, which is the average count or average number of events of a given classification, and this is to the power of C, which is the count or number of events, divided by C factorial times E to the power of NPO, which is the average count or average number of events. Now, for the continuous probability distribution, and this is when you can have decimal places, when you can measure the data, we have seen this is a normal probability distribution. So once again, when we have measurable data, we use the normal distribution, and there are certain conditions that the normal probability distribution will approximate the binomial probability distribution as well. Other continuous probability distributions are the exponential, and this is a distribution that is used in reliability studies, and this is when we have constant failure rate. And the wobble distribution, and this is used when the time to failure is not constant, and they are both used in the reliability field. So chapter 7 is about the fundamentals of probability. So we went over the probability definition. We understood that the 7 different theorems of probability. We reviewed the 3 counting of event rules. We reviewed the different discrete probability distribution, and a quick refresh of the continuous probability distribution that we already saw in prior lectures, which is the normal distribution, and the other 2 are part of the reliability field, and we are going to understand more about it when we cover the reliability chapter later on in this semester.